Alrighty, good morning, guys. Can you hear me?
Yes, we can hear you.
How are we doing?
Great.
Are there any questions before we get started on today's material? And if that's not the case, then we're going to get started. Okay, my computer is not doing this. Try this again. Try a different. Okay. Alrighty, there's my paper. Alrighty, so we are, last time what we were doing was in the very first section here. We're looking at a one-period binomial model. So I'm going to talk a bit more about that. Maybe say a little bit about a multi-period model too. But this is where we're at, right? So instance, Stochastic Calc for Finance, Volume 1, and it's the book by Steve Shreve. We're in the very first chapter. So let's say a little bit more about the one-period binomial model. It's also related to some of the questions in your next homework. So we have a one-period. And the more correct word here will be multiplicative binomial model. So the key component is this random variable. So this is denoted by psi. It goes from our sample space. That's my typically denoted by omega, and then it takes two values. It takes values in R. Like so, omega here. This is our sample space. And in this particular one-period model we're looking at, it typically has the form omega. It has 2 points, omega 1, omega 2. In the homework, there's also one that has 3 points. In the homework, there's an omega that has 3 points, omega 1, 2, and 3. Sometimes you'll see instead of omega 1 and omega 2, you'll see that omega is heads and tails. So we have a random variable. It goes from, so it's a function. It has a domain omega. It has codomain R, and it has a distribution. So the probability that the random variable takes the value u, right? So this here is the probability of either heads or omega 1. This is what we call P, and this is some number between 0 and 1 in a one-period binomial model. And since there are only two possibilities, the probability of psi here being d, this is going to be 1 minus p, which is also a number between 0 and 1. And in the homework, there'll be 3 possibilities in one of the problems. So you have u, d, and then a third value, I don't know, maybe m. And the way that we typically illustrate a binomial model is by these trees. So if this is my random variable, This is my random variable psi. It can either be u or it can be d. So that's the random. This is where all the randomness comes from in a one period binomial model. It comes from this random variable psi that can take only two values. It's the two value component that makes it a binomial model. When you have three values, 1, 2, 3 here, it's no longer a binomial model, it becomes a trinomial model. This here is a trinomial. Okay, so then there's the word multiplicative. Why is it multiplicative? Well, so this here is our model. So our model is, you have a bank. So this is your S. This is the 0th asset. The initial bank price is 1. The value of the bank at time 1, well, this is going to be 1 plus R. And then we'll have, so there's no randomness here. Like that random variable psi that generates all randomness. It is nowhere to be found in the description of the bank. Right, this is the price of the bank account. It starts out being 1 and it ends up being 1 plus R, where R is a constant. Right, and then you'll have the stock. So the stock price starts out being S0, and then it branches. It either goes up or down, and if it goes up, it goes from S0 to S0U, and it goes down to S0 times D. Right, so our S0 is an initial constant, and then our S1, what that is S0 times the random variable psi. Right, so this here is random. There are two possibilities, and the bank account is different. It only has one possibility. But so what we'll write is, what we often write is S1 of omega 1. This is equal to S0 psi of omega 1. And this is equal to S0 times U. And S1 of omega 2, this is equal to S0 psi of omega 2. And this is equal to S0 times D. So there are two possibilities for the stock price. And we talked about if we want to exclude arbitrage, we have to relate the bank and the stock prices. They have to be related at time 1. This here is at time 0. This here is at time 1. Right, and the way that we relate them is by moving this 1 plus R in between these two legs here. So you're going to get S0 times 1 plus R. So U has to be bigger than 1 plus R. 1 plus R has to be bigger than D. All right, any questions on this part? So what we're going to do with this model is to try to price derivatives, right? So if you take a derivative, so a claim, so there are lots of words that mean the same. So a payoff at time 1, this is a claim. There's also some people have derivative. There are many ways to describe the same thing. What this here is again a random variable. It's called V1. It goes from omega into R. Right. This is our payoff. And so it goes from omega. So that means it has there are two possibilities. There's going to be a V1 of omega 1. There's going to be a V1 of omega 2. Right, so as an example, what could it be? last time we looked at a put. We looked at V1. This was, say, was it 5 minus, wait, that's K minus S1. Right, so specifically, what does it mean? It means that, and then positive part, V1 of omega 1, this is equal to K minus S1 of omega 1 positive part, V2 of omega 2, this is K minus S1 of omega 2 positive part. So you're given a payoff, a random variable at time 1. And what we're interested in is figuring out what is the price out here at time 0. So the payoff is given. It could be a put, could be a call, it could be something else. You're given 2 numbers out here. That is, you're giving a random variable. These 2 values that you get out here are these 2 values inside the codomain. And what we're interested in is figuring out what the question mark should be. How much are we willing to pay at time 0 for getting this payoff here at time 1? And the way that we set it up is through this mantra that says pricing is replication. Pricing is replication. And so what does that mean in practice? So construct, this is the number of units. This is the number of bank units. And the other thing you need to construct is the number of stocks. So we construct these 2 such that the wealth, what did I know about wealth X, such that X1, this is going to be the number of shares times the stock price, times the prices, the bank price at time 1, plus the number of shares times the stock price at time 1. Construct these 2 such that the wealth, equals that payoff that we're interested in, V1 then the price, if this is possible, if you can find such 2, if this is possible, the price of getting V1, the price, this is here is at time 0 of getting this thing at time 1 is, well, it's going to be the initial wealth. So this is X0. X0 is the number of shares times the prices. Right, and we normalize the bank account to start out. We normalize the bank account to start out at 1. So we have that. So the name of the game is to create or be able to construct the 2 coefficients, the delta 0 and the delta, such that when you plug them into the formula, you get exactly V1. Right, and what you have here, this is really 2 equations and 2 unknowns, because there are 2 possibilities for V. There's V of omega 1 and V of omega 2. Are we all good down to here? So let me switch over to Mathematica and see if I can show you how to do this in Mathematica. So I'm hoping we can all see Mathematica here. What I'm interested in is, I'm I'm interested in solving equations, so I'll have my delta naught here. And so the price of the bank at time 1 is just 1 plus R. And I'm interested in investing delta into the stock. The stock at time 1 is S0 times U in the upstate. I want this to be V1 of omega 1. That was my first requirement. These are the values in the upstate. And I also have a requirement that in the downstate, in the downstate, I want it to be omega 2. And the only difference is going to be that the value, well, the bank is always the same. So the value of the stock is going to change whether I'm in the up or in the downstate. So this is going to be a D here. And I want to solve these two equations for delta naught, the investment, the number of shares in the bank, and for delta, the number of stocks that I hold. And I'll just go ahead and I'll solve these. And that's the formula. And then what I can do is, I'm now interested in pricing the derivative, and pricing will then be, this will be my x0. And that's going to be what? Well, I need these two. I need these two, so I need delta naught to be this thing. And I need delta to be that. And then the price is going to be what? The price is going to be however many bank units I need to buy. Okay, and the price there is 1. And then delta, this is the number of shares I need to buy, times the share price at time 0. All right, so this here is my initial wealth that is needed to replicate the claims payout, right? And so what is the formula? So here's the long formula. Are there any questions about this part here? So you can kind of see there's something interesting with this formula, because it kind of breaks into two things. There's this 1 plus R. Okay, so that can go outside. So I can write this here as, we call it P tilde. If I write this here as P tilde, and then the first part, I think I'm going to swap the signs around. This mathematic, I put the signs differently. I would want to have a U minus D here. And then I need to swap the signs up here. This is going to be 1 plus R minus D. So that's 1. So that's my P tilde. And okay, express that. So this is going to be the first part that is going to, so I have 1 divided by 1 plus R. Okay, that's downstairs. And then I have P tilde. Then I have P tilde times this W1. That was the first part of the ratio. The second part of the ratio is 1 plus R minus U. Okay, so see what is the relationship between, what is, if I do 1 minus P tilde, and I ask what that is. If I do 1 minus P tilde, and I look at this ratio up here, what I'm seeing is this is 1 plus R minus U divided by D minus U. This is exactly the same thing as 1 minus P tilde. This is 1 plus R minus U divided by D minus U. So I can write this x0 as that thing plus, and then it's 1 minus p tilde times the other thing. These two expressions here, if I ask Mathematica to check that x0 is equal to this, I get true. So there's another way of expressing this x0 that I have here. And it uses these p tildes and the 1 minus p tilde. And so let me try to talk a little bit about that. Where we recognize them from computing the initial wealth that is needed to set up this replicating portfolio. And let me talk a little bit more about them. There are many ways to derive them. This here was one way, but let me try to talk a little bit more about it. Right, so we recognize here that this x0, this turned out to be, it was this 1 plus r that was outside. Right, and then we saw that this was p tilde times the payoff in the upstate, plus, and then it was 1 minus p tilde times the payoff in the downstate. Right, and we had formulas for it. P tilde was equal to, what was it, 1 plus r minus d divided by u minus d. Right, and keep in mind, we had this no arbitrage condition from the beginning. My sheet of paper go. We had this no arbitrage condition here from the beginning, saying that the red dotted line sits in between the two solid legs. So 1 plus r is above d. Right, so 1 plus r is above d. So 1 plus r is above d, u is above d, right? So this here is a number that makes sense. And this here is a number between 0 and 1. So there are other ways of deriving this p tilde. This here is what we saw from Mathematica. This came out by solving to this question, this star here. This equality sign here came from solving star for delta naught and delta. That's how we got this equality sign. Let me show you another way to get these this p tilde. Are there any questions? You guys are very quiet. You're welcome to ask questions as much as you want. There's no way for me to read your mind. I know from past experience, having taught this material a few times, I know that this here is difficult. So if there are questions, please just interrupt and ask. So here's another way of getting a p tilde. And this is more similar to your homework. It says, if I am to compute the expectation of, say, the stock, this is the expectation of a random variable, I can figure out what this is. This here is under p, so I need to put the p probabilities. This was all the way back on the third slide. Right, we had that p there. When I'm taking expectation with respect to the p probabilities, I need to use a little p. And then this is going to be the value that S1 has in the upstate. So this is S0 times u. And then the probability in the downstate is 1 minus p times S0 d. Okay, so that's that expectation. We can compute more expectations. We can also compute the expectation of the discounted stock. So this is 1 over 1 plus r times the expectation of S1. Again, here we're using that there's no randomness in the bank account. The interest rate is a constant. And of course, this is 1 over 1 plus r times what we had just computed. So here we have p's. Now we can switch over and we can also compute the same quantities, but under the p tilde measure. So if I compute under the tilde measure, I put a tilde on top of e, and then I write the expectation of S1. It's basically the same formula. The only difference is that instead of p's, I need to use the other probabilities, the p tildes. And then if I want to discount, I can compute the discounted stock price. And it's going to be very similar to the other one. It's 1 plus r. And then it's the expectation under the tilde probabilities. Plug in the formula we just computed. This is 1 over 1 plus r times p tilde is 0u plus 1 minus p tilde is 0d. Right, so here there are 4 expectations that I have computed. The first 2 involve p, and the last 2 involve p tilde. Right, and when we look at the formula we had from Mathematica, you can see that there are no p's here. There's no p in this expression. P does not appear. That's something to keep in mind. There is no p inside this expression here. There's 1 plus there's r, then there's this p tilde. P tilde is given in terms of r, d, u. So this is only r, d, and u. Just double check that I got it copy pasted correctly from Mathematica. We didn't miss a term. That's good. Okay, so how else would we go about deriving this p tilde? I have these 4 expectations. The way that you can get your hands on p tilde is through what is called a martingale condition. So there's a martingale condition. So martingales, this is something that we have not talked about in this class, and I'm not expecting you guys to know about martingales. We will spend quite some time talking about martingales. And you can see the coming when you're in chapter number 2. This is section 2.4. There's the word martingales, and you can see it's a big chapter. It has like 8 pages in it. So it's a sizable chapter, and it's coming in section 2, in chapter 2, section 2.4. So there's a martingale condition. There's a martingale condition. And the martingale condition is that this last expectation we have here, we are requiring that S0 be equal to, so this here is the martingale condition. We are requiring that this is equal to S1 divided by the expectation of S1 divided by the bank account. And so we plug in what that formula was. It was this thing here. It was 1 over 1 plus r. P tilde is 0u plus 1 minus p tilde is 0d. So this is the martingale requirement. And now what we have here is I want to solve for p tilde and see what we get. You want to solve for p tilde. And what we end up with is, well, you see that S0 is on both sides, so I can cancel that out. I'll have a 1 is equal to 1 divided by 1 plus r. And then on the right-hand side, I'll have P tilde times U minus D plus D. Right, I divide it through where there's 0, and then I put P tilde outside a parentheses, so I have P tilde U, and then I have minus P tilde D. Okay, so the P tilde is outside, I get a minus D. Okay, so then what I'll do is 1 plus R to the other side. I'll move the D to the other side, and then this will be P tilde U minus D. And so I get the formula for P tilde. This is 1 plus R minus D divided by U minus D. And this agrees with that formula we derived from mathematics. That's what we had in mathematics. So this property we're seeing here, this martingale property, one, what it means is that when I compute expectations under these tilde probabilities, the stock grows just as the bank account. And so what does it mean? And we call these for risk neutral probabilities. The probabilities P tilde, and sometimes the other one is called Q tilde. These two probabilities, they are called risk neutral probabilities. And the reason for it is that if I compute the expectation under them of the stock discounted, I get is 0. And this is the same thing if I were to compute the bank account, because this ratio here, this is not random. This is equal to the expectation of 1, which is equal to 1. And so you grow at the same rate. This here is the initial value of the bank account. This here is the initial value of the stock, right? This is the times 0 stock value. And this one here, this is the times 0 bank price. And so under these probabilities, these two price processes, they are expected to grow the same. Any questions on what we're seeing here? But sometimes when you see this material being presented in a classroom setting, everything just works out so neatly. Yeah. No issues. So let me talk a little bit about. So what makes it work? So what makes this model work? Well, you could turn your attention to a question in the homework, and we could start having stuff like a 3 possibilities. So this is a trinomial model. We could even make it worse. We could have like a Gaussian one. We could have a Gaussian model. could be a Gaussian. So like Scholl's model. Right, so here there would be a very large number of possibilities. So we're still sitting here at time 0, and over here this is at time 1, time 0, this here is at time 1. This here's in the homework. This one here, this is really in continuous time. This one here, you're going to see a lot more of in 622 and 623. So in the trinomial model, you could do the same game. So you want to have your wealth. So your wealth at time 1. This is the bank account holdings times the price of the bank account at time 1 plus the stock holdings times the stock price at time 1. Right, and you want to replicate, so you want this to be equal to V1, but in a trinomial model, you have 3 omegas. So what this really is 3 equations. So what this really is here, this is the same thing as saying that. So here you have your omega 1, you want this to be that, but you have 3 of them. You also have number 2, you want this to be 2. Out here is where you have your V1 of omega 1, V1 of omega 2, V1 of omega 3. You're trying to get the right payoff in each of the 3 on each of the 3 branches, and the unfortunate thing is that you only have 2 unknowns. So we have 3 equations. This is the number of elements in omega. In only 2 unknowns, this is the number of traded securities. So this is my delta naught and delta. Right, so you have 3 equations and only 2 unknowns, and this is trouble. In general, you will not be able to solve such equations. So this is a key feature of this model, the binomial model, is that we only have 2. And what that allows us to do, it allows us to solve because we have as many unknowns as we have equations. So if you wanted a trinomial model to have the same feature, what we should do is, so what we could do to fix it, we could add another stock. So that instead of just trading delta naught and delta, you could trade delta naught, delta 1, and delta 2. So this will bring up the number of unknowns from 2 to 3, and then you have a third term here that you have to add. So you have delta 1 here, delta 2 times the second stock price, delta 1 times S1, and then you would have delta 2 times S2, delta 1 times S1, and then delta 2 times S2 valued at omega 3. And so that will give us the same structure as what we had in the binomial case, and it would allow us to gain this the same structure, and this will allow us to replicate and allow us to price. So the reason that my notation is this with this delta naught is that we are ultimately going to be doing this. We're going to be having more stocks, and so my notation is going to be that delta naught is what you hold in the bank, and then delta 1, delta 2, and so on. This is what you hold in these different stocks. Are there any questions or comments on this part? But so the next thing that's coming is looking maybe a little bit at the multi-period binomial model and how to set it up. Let me say a little bit about that. So the multi-period binomial model so now the randomness is now going to come from a more general structure. So randomness comes from the size. We want to have psi. We want to have psi 1, psi 2. If it's an n-period model, then you want to have n here. So there are n conflicts. We will also have a need to look at an infinite string. So now here there are infinitely many conflicts. This here comes a little bit later. This comes a little bit later in the textbook. I'm hoping we'll get there. This is over here in this is in section 5. This is this random walk. You can see there's a word that's called perpetual. Perpetual means infinite. This here is for the this is here is in section 5. This is the word perpetual. So this is going to come towards the end of the course if we get that far. So we have randomness coming from these conflicts. For now, we'll have capital N conflicts, so 10 conflicts. And the assumptions that we're going to make is, in this case, we will have that psi 1, psi n. I have a finite number of them. They will be IID. Okay, so I'll need to explain what that is. The IID Bernoullis. Right, so Bernoullis, this is what we're used to, right? So psi n will have these two values. It will go up with the probability p. It will go up to u. And then go down with the probability q, which is 1 minus p. So the IID Bernoullis, and so what does that mean? Well, the first I, this means identical. And the last two means identical and independent distributed. Right, so that's the first I, that's the second I, and that's the IIDs, the identical and independently distributed. Okay, so what does it mean to be identically distributed? Well, it means that they all have that distribution. Here, what does it mean to be independent? Well, what it means to be independent, there are several ways of saying this. The way that it works well for independent means that in this course, maybe also in others, is that if I look at the characteristic function, so the exponential of I, and then let me put in some variable here, say A1 times psi 1 all the way up to I times A n psi n. So this is the joint characteristic function. The joint characteristic function maybe I should say a little bit about that in a minute, but so the property is that the joint characteristic function factors into a product of the individual ones. Maybe I should use I here, maybe I should use N. Too many I's. Right, and these are all the same because they have the identically distributed property. So when I'm talking about independence, this here is what independence is about. That I have when the variable, the independent, if the joint characteristic function has this product structure. And so I'm hoping that everybody has seen the characteristic function at some point in their lives. And if not, this is something that is going to become an important part of the MS of your courses in quant finance. You might have seen, so maybe we should just have just recall a bit of probability. If I have a random variable, let's say X, right? So this is a random variable that goes from omega into, say, R. Right? We say the moment generating function, the moment generating function has the form an expectation under, well, here we're working under P of e to the ax. This is the moment generating function. Right, so x is real valued, a here is a number, a here is a number. So this is the function, a here is a number in, say, R. And the problem with the moment generating function is the following. So the potential problem is that this moment generating function that it belongs, well, it's a this is a random variable which is positive, so the expectation is going to be positive, but it could blow up. So this here is the potential problem. That infinity is a possible value of the moment generating function. Maybe to look at an example. So the example that is going to be used a lot. This is used a lot in 621, 622, and 623. I've gotten feedback from students that said that they wished that it had been made clear to them early on the importance of moment generating functions and characteristic functions. So I'm telling you guys now, moment generating functions and characteristic functions, they are really important in these courses. They are being used a lot in various forms and shapes. So they are important. So don't neglect this. This is something that is, there are some things we don't have to do using characteristic functions, but it's coming. It's coming when I'm teaching 623 in the spring. There'll be lots of problems that we can only study using these characteristic functions. So they're used a lot. So maybe just an example. I said one of the most standard example is to take x normal, mean and variance 0 and 1. So the first entry here, this is the mean. And the second entry, this is the variance. So a standard normal, that means that if I'm looking at the probability distribution, the probability that x is less than some number, I can compute that simply by integrating the density. And the density for a standard normal is this course function. This is e to the minus 1 over 2, say y squared dy. And this is true for any x in the reals. Right. So how would I go about, what is the potential problem here? Well, one thing I could do is, if I wanted to compute the moment generating function, what I'll have to do is to compute this random variable, I will use the density function. And so this is the distribution. To get the density, I need to compute the derivative with respect to little x. And so I can write this here as an integral over possible values of the random variable. So it will be in R. I'll have e to the a, and then maybe I'll call this for x. And then I'll plug in the derivative of the distribution with respect to x, and this is going to give me the density. This is 1 over root 2 pi e to the minus 1/2 x squared and dx. So how would I compute this integral? Well, again, the easy and dirty way to do it is just let me show you if, let's see if Mathematica can do it. Mathematica can do it, and maybe we're in good shape. Otherwise, we'll do it by hand. So again, if I look at Mathematica and I wanted to integrate, I'm interested in having it integrate x of a times x times x of minus x squared divided by 2. And then I also need to divide by square root of 2 times pi. Right, that was the thing that I want to integrate. And I want my x's. I want my x's to go from minus. I want my x's to go from minus infinity to infinity. Like, that's what I'm interested in. What could this integral be? Mathematica says it's the exponential of a squared divided by 2. Okay, so Mathematica can do that. Let's see if we can do it on a piece of paper as well. It's e to the a squared divided by 2. And if I go back here, can I derive that? Well, I think there's a chance I can put this thing here outside. This is 1 over root 2 pi. And then I'll have an integral over r. Then I'll have 2 exponentials. So the product of 2 exponentials is going to be the sum. So this is going to be ax minus 1/2 x squared dx. Are there any ideas on how should I get this thing? What should I do next? When I see something like this, what comes to mind? Complete the square. Awesome. This is exactly what we should do. We should complete the square. We should complete the square. So I should do minus 1/2, and then I should have x minus a, and then a square. And so now the equality sign is not true. What ends up happening is that I have an a squared here, and then minus 1/2, so I need to have plus 1/2 a squared and dx. So now the equality sign is good. I can move, this one here has no x dependent, so he can travel outside. And out here he's sitting there in the front, and then 1 over root 2 pi integral over r. Well, let's have a look. What I could do here is I could substitute y to be x minus a. And then I'll have that dy dx, this is 1, so Jacobian. Jacobian is, I don't have to worry about it, it's equal to 1. And when x is equal to minus infinity, y is equal to minus infinity, and so on. So this is really an integral over r, and here I get e to the minus 1/2 y squared dy is equal to dx. And so here I have an integral of the density function. This integral here is equal to 1. This is equal to 1. And so I'm left with this expression, e to the 1/2 a squared. And this was also what Mathematica got. So I'm comfortable that this here is the moment generating function. This is a moment generating function for the normal. So where's the problem then? Well, the problem that comes in, we could do another example. Like I was highlighting this thing, right? This one here is finite, right? This is finite for any a in R. But I don't have to tweak it very much. If instead I would look at the moment generating function for this square of x, moment generating function for the square of x, then it becomes a different story. And so I'll move along the same lines. I will write an integral. I'll plug in the density. I'll move along the same lines. I'll plug in the density. But now I have a square here. And then I'll have the Gauss function. And now what? Well, when is this finite? What you want to do is you want to look at I have e to the ax squared, and I have minus 1/2 x squared here. So I can combine these two in there. Combine these two into an e to a minus 1/2 x squared. When is such an integral finite? Well, to get your hands on it, you can plug in some random values. If I take a to be 1, if a is equal to 1, then I'm asking about the integral of e to the, so a minus, so this is 1 minus 1/2, this is 1/2. If I integrate something like this, what do I get? No. That's when I have a minus sign here. I get square root of 2 pi. What do I get when I have a plus?
Wouldn't it just go to infinity?
Yep. So that doesn't work. What about if I put in a 1/2 here? For what I get here, then I'll have a 1/2 minus a 1/2. This is a 0, so exponential of a 0. This is 1. What would I get here?
Infinity as well.
So what's the condition?
It has to be less than 1/2.
Right, so that's the one. So should we just go back to Mathematica and see if Mathematica can figure this out too? So let's see if Mathematica can do this one. Right, so it's almost the thing that we had. It's almost the thing that we had. The only thing we have to change is, instead of integrating a times x, I have to integrate a times x squared. Right, and now the condition was that a has to be less than a half. This is what we should expect. Let's see what comes out of Mathematica, if anything. There it is. And you can see there is the condition that a, so here Mathematica is allowing for, it's allowing for the possibility that a is a complex number. So it says that the real part of a has to be less than a half. And then so there's the formula. And before, the characteristic function would have this nice expression. And if you put a square, then you're going to get this expression. And you can see the trouble happens downstairs. It's when 2 minus 4a becomes equal to 0, then you're dividing by 0 and you have a problem. So the problem that I'm highlighting here, this is not some crazy thing. In general, this can happen quickly. It can happen simply by taking a normal and squaring it. It's not going to happen in these models where I only have 2 possible values. You're not going to run into this issue here. But as I said, these courses, in particular 622 and 623, they use Gaussian random variables all the time. Underlying Black Scholes, you find Gaussians. So then this becomes an issue. So the way around that, one way around this problem is to focus on characteristic functions. So the characteristic functions do not have this problem. So characteristic functions, they don't have this problem. Right, I take a random variable, it goes from omega into r, and then what I'm looking at is the expectation of a I x. This here does not have the ability to explode. And the reason that it doesn't have the ability to explode is if you take absolute value here, and if I move the absolute value inside, I'm going to get a bigger number. E I A x. So we need to remember what is this number up here, right? So we need to remember. I mean, this is some version of polar coordinates. If I take a number, in R2 or in the complex plane, so I have A here, I have B here. So my Z, if it's a complex number, then I'll write this as A. So this here is the real part. This one here would then be the imaginary part. So here I have IB. So the complex plane, R2, polar coordinates are typically what you refer to in R2, but it is really very similar. So this here is my vector. So there are different ways of expressing an element in R2. One way is to express it in terms of the coordinates, the x coordinate and the y coordinate. But another way to express it is as an angle, as a theta, right? And then as a length. Those are 2 equivalent ways of expressing it. So I could also write this here as, let's see, on the x-axis, is this where we have sine of theta plus I cosine of theta, and then we need the length to come in here. And you can also write this here as the length times E I theta. So a number in R2 can be expressed in terms of an angle. Theta here is something that runs between 0 and 2 pi, and Z is something that runs between 0 and infinity. I forget, though, I always mess this up here. Is it cosine first and then?
I think it is
Cosine first.
cosine first.
Yeah, cosine first.
So here's the thing, I've taught this for so many years, and the mistake you see me make here, I think I made this, I make this mistake here more times than I get it right. Somehow over my head, it's always swapped. So when you see stuff like this, just please hit the button, because this is one of the places I make mistakes. So how does one remember something like this? So you would,
You can say if theta is 0,
yes,
then it will be just
exactly.
real.
So exactly, take theta to be equal to 0, then cosine of 0 is then going to be 1 or 0, and this is the way to back it up. Okay. I mean, at the end of the day, it's just we have decided to call one cosine and the other one for sine. As humans, we could have decided to call them the opposite thing. So the equality between EI theta being equal to this cosine plus I sine theta, this is called Euler's form. And one way to see that Euler's form is correct is exactly as being mentioned here. What you could do is to check it. You could take out theta equal to 0 and see that both sides is equal to 1, right? EI theta, that's going to be E0, so that's going to be a 1. And so this is where you can see that I messed up, because I cannot have any i's here on the right hand side. I should just have cosine of 0, that should be my 1. So that's one way to do it, and then that's one way to check that, get these things right. And then the other thing that you need to do is you need to compute the derivative, right? So to see the two functions are the same, it suffices to check that these share a point, and then check that these two have the same derivative. Right, so if you can remember how to differentiate cosine and sine, check that these two are the same. So that's Euler's form. And one thing that you can see, like the length here, this is going to be equal to a squared and b squared, and then the square root. And so what does all that stuff down here have to do with the problem that I'm mentioning for characteristic functions? Well, it's the fact that the length of such a vector here, the length of this guy here, what is it going to be? Well, it'll be cosine squared plus sine squared added up, take the square root, right? That's the formula for the length, modulus. But cosine squared plus sine squared, this is always equal to 1. Right? And the square root of 1 is 1. So what you're going to get here is that this is always bounded by 1. Which is the characteristic function is never going to blow up to a plus infinity. And the price that you're paying, so the price you pay, we pay to keep the characteristic function finite, to keep the absolute value of e to the ax less than 1, is, this is the price. I mean, there's always a price to be paid. it really is that when I look at the map that goes from R into EIAX, this thing here, this is a complex number. This is a complex number. This is not real value. So characteristic functions in general, you're not real value. But okay, I'm hoping we can work with characteristic with complex numbers as well. And maybe we should just return to Mathematica and try to compute these expressions, but for the characteristic function. So here we were integrating. This expression. So let me see. I think it's I. Is that the right one? No, that's not the one. So capital I. So there you go. If I am to calculate the characteristic function instead of the moment generating function for the standard normal, you see what happens is that you get a minus sign. You get a minus sign. So instead of having the exponential of a squared divided by 2, you're going to get the exponential of minus a squared divided by 2. And that has again a lot to do with the this has a lot to do with this bound that we just derived, because there's just no way. So let's go back to an example. If I have x to be standard normal, you cannot have the same formula. This cannot be equal to a squared divided by 2, right? Because this violates the bound. This here violates the bound that you have up here. So this is impossible, and the correct answer is to have a minus sign there, right? And then this is indeed less than 1 for any a in R. We could also have the square one. This was the troublemaker. This was the one that was only finite for some. If we go over to Mathematica, I see if Mathematica is willing to do that one too. So instead of the one we had here, the only thing that changes is we put a square, and then you see what we get here. It's going to be something that has the same flavor as what we saw above, but let's see what Mathematica says. So we're going to get the square root 2 divided by the square root of 2 minus 4ia. And you can see the condition now. The condition now is different. When we looked at the moment generating function, it was the real value of a should be less than a half. But now the condition is different. It says that the imaginary part of a should be bigger than minus 1 over 2. But for us, a is already real, right? So a imaginary part is equal to 0. So that condition here that Mathematica has listed, this is valid because for us, a is real, so the imaginary part is equal to 0, and 0 is bigger than minus 1 over 2. So we have the formula for any a in R. So we were able to circumvent the explosion to plus infinity, but the price we're paying is that we have an I now inside our expression. We don't have it up here. In the first one, there's no I. The standard normal characteristic function is a real value. There's no I here, but down here for the x squared, we do see that there is I dependence there. Okay, are there any questions about what we've seen here? So again, let me stress here that these characteristic functions, if you have not seen them, then it's a good time to brush up on them a bit, because they really are going to come. They're really going to come in this course, and they're also going to come in other courses. So there are of course many ways. There are many equivalent ways of. Camera disappeared. There are many equivalent ways of writing the independence property. And here I'm using characteristic functions to express this independence property. It says that my joint characteristic function, so when you have multiple of them, so A1, this here has to be true for any A up to AN in R. When I have this property, I'm independent. You could also have written, things like, equivalently, you could have written stuff like P of psi1 being in a set A1 up to psi n being in a set AN, that this should be equal to the product. I could have written that these two properties, they are equivalent. I wrote the top one because this is when you go ahead and you check for independence. This is, in my experience, this is one of the easiest ways to check for independence. And I'll also do it, I'll do that probably next time already in the, we're going to need this property here in the binomial model, in the multi-period binomial model. So I think this one here is more the equivalent, of course, but this using characteristic functions, this tends to be easier to make work than the bottom one. Are there any questions or comments on characteristic functions before we have a little bit more time before the break? So let me just say a few words about the what is happening in this multi-period binomial model. We have these coin flips. Now, how do we create the model that we're interested in? Well, basically what we're going to do is we're going to stitch together. A bunch of one-period models. So for a two-period binomial, the way that we're going to stitch it together is we're going to grow our tree. So this here was at time 0. And this one here was at time 1, and we're going to have a time 2 over here. And so the way we want to do it, this was what we used to. We'll grow one more, and then we'll grow one more. We can also grow. Of course, we can grow as many as we want. We can grow all the way up to time n. So we want to say that. So we have S0. Then we're going to have S1. This is where the multiplicativeness comes in. Right? So you have S0 times psi1. And then you're going to have S2. This is S1 times psi2. Or if you want, this is S0, psi1, psi2. And so we can see now we have how many possible values do we have? Well, it depends on how many possible values do we have of these two. So this one here can be U, this one here can be D. Then the next one can be, well, it can be U or D. So this could be U, U, and then it could be U, D. And then it could be D, U, and it could be D, D. And because U times D is the same thing as U times D is the same thing as D times U, what we end up with here is S0 U, U, and then these two will combine back together. This would be S0 U, D, and this one here would be S0 D squared. Right, so this property that they combine back in the middle, this is called a recombining tree. And you can see it gives us three values. Whereas if we would have a non-recombining tree, we would have, this is non-recombining. And you would have 4 values. And you can see this can very quickly get out of hand. If I were to put one more period on it, then I would have how many would I have? Then I would have 1, 2, 3, 4, 5, 6, 7. I'll have 8. Whereas if I would look at a recombining tree over here on the left, what I would have in a, this is at t equal to 0, t equal to 1, t equal to 2, and t equal to 3. This is a 3-period model. If I would look at a recombining 3-period model, it would be simpler. I would go up and then down, and then it will recombine here. And then t equal to 2. Then I'll go up, down, up, down, up, down. And this is t equal to 3. So here I'll have 4 values. Right, so one of them grows much faster. This one here grows linearly. This one here grows exponentially. And the version of the binomial model that we're looking at is going to be the one that recombines. So a 2-period model, this one here is a 3-period model. So how would one go about studying such a model? Well, the idea, of course, being that we should try to reduce it to what we have learned. And the way to go about that is using dynamical programming. Some of you might have heard about dynamical programming in like a computer science class. Some words that you will hear me use will be something like dynamical programming. You'll also hear something called backward induction. The way you go about studying a multi-period model, it's always the same. So you start at the last period. Okay, so you start at the last period. So if you're looking at a 3-period model, in this recombining world, right, so you start at the last period. So this here is t equal to 2, and then t equal to 3. And what you see now is up here in the corner, this here is like a 1-period. This is a 1-period model. There's a different color. This here is a 1-period model. I think I'm out of colors. Maybe there's another color here. And this one here is a 1-period model. So within each circle, you have exactly what we've been talking about earlier today and what we talked about last time. So you can price a payoff that's coming out here, and you can figure out what the price is here. Likewise, payoff that's coming here and coming here, you can figure out what the price is here, because it is a 1-period model like the one that we studied. And likewise here, if you have a payoff coming here and a payoff coming here, you can figure out what the price is over here. So you move in this direction. You start here at the end. And this is, then you perform the analysis for these three models that we have done already. And this will give you this number, and that number. And then you move one to the left. Now you have a model here. You have a model here. So this will give you, and now I am out of colors. There's the yellow one here. This will give you these three values, and then you can go one step back here on the yellow. Can't see that one. And you go one step back here. This will be your new model, and this here will be your new model. So you will be able to go from here, and this will give you a number there. You go from here and there, and this will give you a number here. And then finally, you will be out here in the key, right? The goal is to figure out what this question mark is. And the way you go about doing it is moving in this direction. So you go from T3 to T2 to T1 to T0. And so you can see it breaks down to 1, 2, 3, 4, 5, 6. It breaks down to six one-period models. So the calculations that you have done in last week and also earlier today, you have to do 6 times as much work. And then you can deal with a three-period binomial model. So we'll do a lot of that. We'll do examples next time. So this is next time. Okay, I think this is a good time to take a break. Are there any questions on these binomial models, multi-period or single period?
Can I ask one quick question about where you got the 6 one-period models?
Yeah.
So is the last one from T0 to T1?
Yes. There's one more sitting out here. Right? So you go from here to this point. You go from here to this point. You go from here to this point. That was 3. Then you go from these 2 points to that point. You go from these 2 points to that point. That was 5. And then you go from these 2 points to this one. This is the last one.
Okay, thank you.
Right, when you move in, the essential part is that you move in. This here is the direction that you solve in. You solve in this direction. And this is really what dynamical programming, or you can see it's called backward induction. So you start out here at the end, and then you move in this direction. It never works going in the forward direction.
Okay, thank you.
Yep. Are there other questions? All right, let's take a little break and then get back together. There's going to be a different Zoom link, but we tried all that before. So I'll see you in 10-15 minutes.